Hello, thanks for tuning in. Forth is a programming language with the usual features, conditionals, loops, functions, and so on. But in some ways it is simpler and more self-contained than the popular languages. A Forth system may be small enough that you can read and understand the whole thing. I wrote a Forth interpreter in x86-64 machine code. It's a standard Forth. It meets the Forth 2012 standard, so you can use the standard document as a reference. Forth can run on really small machines like microcontrollers. Features like floating point arithmetic are not part of the core language. This particular Forth has no floating point arithmetic, no local variables, and no file access. I just haven't implemented them yet. SmithForth runs on Linux. It makes Linux system calls. It should run on Windows by the Windows subsystem for Linux, but I haven't tried it. This is a subroutine threaded Forth, which I think is the most straightforward way. We use the processor's call and return instructions. The Intel manual is our reference on the processor. SmithForth begins with handwritten machine code. I use VI to edit text files and XXD to convert between text and binary. That's about it for the tools. No C library, no assembler, no linker. I made a video series on 32-bit handmade Linux x86 executables. If you want to understand SmithForth, that's a good place to start. Now we're going to look at the SmithForth source code from beginning to end. Please find the source code on my webpage. SmithForth consists of two source files. sforth.dmp is a text file. You might call it a hex dump or an annotated hex dump that we convert to a binary file. The resulting binary is a primitive Forth system of about 1,000 bytes of machine code. The other file, system.fs, is about 1,000 lines of Forth that extend the primitive Forth system to a standard Forth system. The elf header contains information about the executable, notably the entry point of the process. entry equals 00400078. That's right here, where we have a simple interpreter. Before we go on, let's discuss the plan. Programs are organized in subroutines. Here's how subroutines are handled by a machine like the x86. To enter a subroutine is to get the current value of the instruction pointer, push that value onto the x86 stack so we can find our way back, and set the instruction pointer to the entry address of the desired subroutine so that execution jumps to there. This is all done by x86 instruction call. To leave a subroutine is to pop a number from the x86 stack and set the instruction pointer to that value so that execution returns to a place in the instruction stream from where a subroutine was called earlier. This is all done by x86 instruction ret. With call, we must refer to a subroutine by its address, like 10000047. But as programmers, we really want to refer to a subroutine by its name, like plus or compare. Forth associates names to subroutines by a device called the dictionary. Dictionary as in something that lets you look up words. There are many ways to implement the Forth dictionary, but however you do it, there's a sequence of entries where each entry is essentially a named subroutine. Early entries are basic subroutines, and later entries are often more complex subroutines. Typically, the dictionary grows toward higher addresses of the Forth dataspace, and we keep track of the address, here, of the first unused byte of the dataspace, and the address where the latest dictionary entry begins. Each dictionary entry knows the address of the next earlier dictionary entry. To search for an entry in the dictionary, we start at the latest entry and follow next earlier links until we reach an entry with a matching name. To add an entry to the dictionary, we write a header and the new subroutine at here, and we update here and latest. Our plan is to add some useful words to the dictionary. We will write the subroutines ourselves in machine code. We just want a little help with keeping the dictionary structure. We're going to write 3 interpreters. First, a binary interpreter that deals with a binary input stream, byte by byte, with a few commands to help us manage addresses. Then, a primitive Forth interpreter called the text interpreter that recognizes whole words made of non-white space characters. And finally, a proper Forth interpreter. For the binary interpreter, here's a loop that deals with a stream of bytes. We fetch a byte from the input stream, we write that byte to the output stream, and repeat. The byte itself goes in register AL. If we want to do something with the byte, we can insert more instructions between instructions load and store. Register RSI points to the source of these bytes. The source is the rest of this binary file, beginning right after the binary interpreter. Register RDI points to the destination of these bytes. The destination is the fourth data space, where the dictionary goes. This binary interpreter has commands to execute a dictionary entry, to create a new dictionary entry, and to compile a call to another dictionary entry. In the input stream, each command begins with byte 99. The byte after command byte 99 determines which command is issued. Some commands refer to an existing dictionary entry, let's say an old entry. Some commands declare a new dictionary entry. When we select an old entry, we use only the initial character of its name to identify it. Characters used in names must be in the printable range of the ASCII code, 20 to 7F. All these have bit 20 or bit 40 turned on. When we declare a new entry, we provide its full name. Names in Forth have various lengths. In SmithForth, names are 31 bytes long at most, so that 5 bits are enough to keep count. The programmer provides the length of the name in the argument byte, and then the full name after that. A number less than 32 has bits 20 and 40 turned off. So here's how the binary interpreter works. It's a loop. Each time through the loop, we read a byte. If the byte does not indicate a command, we transmit the byte unchanged. If the byte is a command, we fetch the next byte as our argument. If the command defines a new word, then the command is handled by subroutine head. If the command refers to an old word, we traverse the dictionary from latest to early, looking for an entry whose name's initial character matches the command argument. When found, we compile a call if bit 80 is off, or execute the word if bit 80 is on. Now, the interpreter relies on these subroutines compile and head, and it reaches them by x86 instructions jz-rel8. So just this once, we compute jump lengths by counting bytes. Input to the binary interpreter begins at 004000B2. Compile and head are not only subroutines used by the interpreter. Compile and head are the first words in the dictionary. See here byte 99 for a command. 05 indicating a new definition whose name is 5 characters long. The 5 bytes 43, 4F, 4D, 50, 4C are the name compile encoded in ASCII. Compile is essentially Forth's compile comma. Compile writes a single x86 instruction to the interpreter's output stream. That instruction is what Intel describes as call near absolute indirect the address given in RM64. We're using an addressing mode with an SIB byte indicating a 32-bit displacement, a DISP32. The instruction contains an immediate 4-byte address. In memory, at that 4-byte address is an 8-byte address, the entry point of the subroutine. This will all be clearer in a little bit when we look at some concrete examples. The second word in the Forth dictionary is head, whose job is to write a dictionary header. The header consists of a code field containing the address of a subroutine, a link field containing the address of the next earlier dictionary entry, a flag byte including the length of the name, and then the name. After the name comes the machine code of the subroutine. This subroutine includes a call to another Forth word named type. So here we are at head, whose job is to write a header. We advance the output pointer to the next multiple of 16, just so the debugging output looks nice. We write the execution token of the old latest word into the link field of the new entry. Latest is a variable at the beginning of the Forth data space, whose address is in register RDX when head is invoked. And we record the current value of the output pointer as the latest. We write the flag byte, which is in register AL when head is invoked. We read the length of the name from the low 5 bits of the flag byte and copy that many bytes into the name field. And now we've reached the end of the header where the subroutine begins. We record this address in the code field of the header. By is just a Linux syscall exit. Here's a little guide to making Linux syscalls. To do a Linux syscall, we set up some registers and issue an x86 instruction syscall. The Linux syscall number 3C for exit goes in register RAX. Arguments to a syscall go in registers RDI, RSI, RDX, R10, and so on. Syscall exit has only one parameter, the exit status. We set RDI to 0 for normal exit status. And now we can run the executable by an interpreter command. We have 99 for the command. We want to execute by, whose first character is B, ASCII 42, plus 80 to execute equals C2. Here's how we make this file into an executable. This script, make.sh, you don't need it if you're using SmithForth or building SmithForth from the source code. But when we're working on the SmithForth system and the size of the binary changes, we have to update the p file size field of the elf header, and that's what this script does. The executable is made, we run it, and it finishes with exit status 0. I know that may not seem like much, but when you're starting from scratch, it's something. Next word is type, which uses Linux syscall write to put data out to the standard output stream. This subroutine has a loop. According to the man page, the write command might succeed only partially, and in this case, we try again to write the remaining data. If you experience a partial write because the device is full, who knows, the loop may go on forever. There are not many safeguards in SmithForth. Writing machine code by hand, it's easy to make mistakes. So we developed debugging tools as soon as possible. DBG is a word to display the fourth data space. The fourth data stack grows toward lesser addresses from the beginning of the fourth data space. So with one syscall write, we can see both the data stack and the dictionary. Here's our first invocation of another fourth word. 99 for a command and 54 for ASCII T. We run that and use XXD to convert the output from binary to text. Here are 4 cells of the fourth stack. Another 6 cells hold system variables. Here's the first definition. You can see the name compl on the right. First is the code field. In Big Endian, 10000046 is the address where code begins. Why does code begin there? Well, it's right after the name. There's a flag byte, including the length, followed by the 5 bytes of the name. The link field is 0, as the first entry in the dictionary has no next earlier entry. Here are the x86 instructions. Next word is head. We skip forward to the next multiple of 16 to start the entry. We didn't write these zeros. These locations are unwritten. Linux provides zeros in the part of the memory segment beyond the bytes of our binary file. Code begins at 10000075, right after the name, and the link is 10000030, where the next earlier entry begins. Back to the source code, I have a word reg to display the contents of all the registers. Now it's time to start writing the text interpreter, which is just a Forth interpreter with some limitations, like only accepting numbers in base 16. Forth is pretty flexible about how you format your code, so you might think all whitespace is the same, but it turns out that lines are important in Forth. For instance, when you use colon to define a word, the name that comes after the colon should be on the same line. So Forth is line-oriented, and I try in SmithForth to do things the Forth way. Of the system variables, num_in contains the number of characters in the current line. TIB contains the address where the current line begins. toIn contains the number of characters in the current line that have been parsed. In Forth, a parsed character is one that has been removed from the input stream. Refill fetches a line into the input buffer. Normally the Forth input would come from the keyboard or a file, but to get started we read the system Forth directly from the executable without a syscall. So a line is just a range of bytes in the executable, and refill updates TIB and num_in according to that range. We have parsing words, useful for recognizing word boundaries in the input stream. Left square bracket puts the system in interpreting state. Right square bracket puts the system in compiling state. Backslash begins a comment that runs to the end of the line. No need to read the remaining characters in the line, just designate them all as parsed by setting toIn to num_in. Left round bracket, or parenthesis, begins a comment that ends at the next right round bracket, or at the end of the line, whichever comes first. Parsing words can do this. Colon is a word to start a new definition. We call a parsing word to get the new word's name. Some registers need to be set before head is called. Normally in Forth you would put such input on the data stack, but we haven't fully made that transition yet from registers in machine language to the data stack in Forth. Colon also sets the hidden bit of the flag byte, so this word cannot be found during its own definition. This is a normal Forth thing that allows a word to refer to an earlier word of the same name. Semicolon comes at the end of a colon definition. We write a return instruction and turn off the hidden bit. Normally the word dot displays an integer, but for now, dot compiles a byte into the Forth data area, like the Forth word C comma. Lit compiles code to push a number onto the Forth data stack. It's an 8-bit number that becomes a 64-bit number by sign extension. This turns out to be useful sometimes and irritating sometimes, but it keeps the implementation simple. The next word, xt=, determines whether a given dictionary entry is the one we're searching for. This entry is not the one we want if it is hidden, if the length of its name is wrong, or if the characters of the name are wrong. Find works by applying word xt= to each dictionary entry from latest to early. Num converts a string of hexadecimal numerals to a number. A dictionary search could yield a hit or a miss. In case of a miss, the text interpreter treats the word as a number and does the usual Forth thing. When interpreting, the number stays on the stack. When compiling, we call lit to compile code that pushes the number onto the stack. Exec takes a Forth execution token and executes it. It works by first compiling a subroutine call and then executing the newly written call. If that sounds odd, let me explain. SmithForth is subroutine threaded with call near absolute indirect the address given in RM64 and an immediate 4-byte address. Forth has special words create and does. For most words, the code field points into the word's own dictionary entry, but created words have their code fields redirected to a single instance of a certain subroutine. I don't think this is required in standard Forth. It's just how you do things efficiently in the Forth tradition. When a created word is called, the system needs to find the called word's dictionary entry. The return stack contains a pointer just past the end of the instruction that called the word. With our call near absolute indirect scheme, the 4 bytes before that are the address of the called word's dictionary entry. Great, but that's for a compiled call. We can also call a word directly from the interpreter. If we did this by an instruction like call rbx, as in the binary interpreter, then the trick would not work. One solution is to make executed calls work like compiled calls. Therefore, exec compiles a call and then executes it. This lowercase exec is a conditional version of uppercase exec. Why do we need a distinct dictionary entry? Well, we have a certain way of compiling calls. Each compiled call is an instruction 7 bytes long. However, SmithForth is experimental. We are trying various ways of compiling calls, and not all of them are 7 bytes long. So we're writing machine code that generates compiled calls of unknown length. At the same time, we're implementing flow control by jumps whose lengths must be known. We have a problem jumping over compiled calls, and one solution is to wrap the compiled call in a subroutine with 2 exit points. Similarly, we have a conditional version of compil. Hit is for when an entry is found in the dictionary. The entry is executed or compiled depending on state and whether the word is immediate. Sval is like Forth's evaluate, whose job is to interpret a text string. Sval interprets the string in the input buffer. We parse a name from the buffer, search the dictionary, and handle a hit or a miss, and repeat until the buffer is fully parsed. Now the text interpreter just needs to refill the input buffer, evaluate it, and repeat. Our final act of the file is to call the text interpreter. File system.fs contains the rest of the system. It's written in Forth, although much of the Forth is dedicated to writing more machine code. We have some comments on the design of the system. SmithForth is supposed to be a Forth 2012 system, providing the core extensions word set, providing the double number extensions word set, providing the programming tools word set, providing selected words from the programming tools extensions word set. Now let's see the Forth code. We have 1 plus with a single x86 instruction increment. These bytes, 49FF07, are compiled right into the definition. 1 minus, 2 times, 4 times, 8 times, 2 div, negate, invert. These operate on the cell at the end of the stack, or the top of the stack as they say. That's R15. Then we define backtick, kind of a companion to dot. Dot compiles a byte. Backtick compiles code that compiles a byte. Backtick is useful in words that we might call assembler words. Plus equals compiles code to adjust the data stack pointer. Plus plus equals compiles code to adjust the return stack pointer. It's nice to have a div mod operator for some of these x86-64 instructions, as the 4 bits that identify a register may be distributed to 2 places, 3 bits in the mod rm byte of the instruction, and 1 bit in the rex prefix byte. Up compiles code that copies a cell from a register to the 4th stack. Down compiles code that copies a cell from the 4th stack to a register. Up and down may refer to any of the 16 general-purpose registers, and to any location within a dozen cells of the end of the stack. So, for instance, we can implement plus as follows. Download the cell at the end of the stack to register 0. That's RAX. Shrink the stack by 8 bytes. Now the top of the stack is the other addend. Add RAX to the top of the stack. That's 3 machine instructions, all compiled immediately into the definition. Here's a redefinition of type. The original type takes its arguments from certain registers, while the 4th type should take its arguments from the stack. So we download stack plus 8 bytes, the address, into register 6, that's RSI. Download stack plus 0 bytes, the length, into register 2, that's RDX. Shrink the stack by 16, then call the old type. The old type messes with register RDI, but RDI is the data space pointer, so we save and restore RDI, register 7, on the return stack with 7 push and 7 pop. Now we're in business, implementing Forth words in Forth. These stack manipulation words like drop and 2 over are straightforward applications of up, down, and plus equals. We have recursion, comparisons, conditionals and loops. I wrote these words 0 meaning if 0, ever meaning always, jump to compile a 4-byte dummy value rel32 and issue a forward reference. So for example, if is 0 jump, again is ever jump back, and I can almost understand how forth works. Create and does don't require much code, but they are challenging to understand. I put some links in code comments, and right away we have a few applications of create and does to look at. Variable is create 0, comma. Constant is create, comma, does fetch. Value is a little trickier, as it has to work with to, and to also works with toValue, for instance. My solution is that each entry created by value or toValue has a 1-byte identifier to assist to in resolving what it needs to do. Arithmetic again. Forth is often implemented with 16-bit cells, which is kind of small for integer arithmetic. So it's customary to provide some double-celled arithmetic operators. I implemented the optional double number word set. One of these words, m times div, has a triple-celled intermediate result to hold the product of a double-celled multiplicand and a single-celled multiplier. So as we implement this traditionally 16-bit programming environment, we end up writing an arithmetic operation with a 192-bit result. We have symmetric division as provided by the machine, and floored division as in mathematics. C is essentially a disassembler. Here is C compile. We get a view of the dictionary entry with the code field, link field, flag byte, name, and the subroutine, 1 instruction per line. Looking at head, we see many bytes that are labeled unknown, even though these are valid machine instructions. That's because my disassembler tool is incomplete. However, it is really useful for looking at words defined with control structures or other automatically generated code. We define a word with an if statement, here's how it appears in the ordinary debugging output. But C divides the code into distinct machine instructions, making it easier to read. The first 3 instructions push the number 5 onto the data stack. Then the stack shrinks by 1 cell, and we compare the entry just off the end of the stack to 0 and jump if 0. There is 0 and jump, altogether if. The disassembler shows the jump length plus 7. Why 7? Because that's the length of the if block, call CR. There is no code here corresponding to then. Then work to compile time to figure out the length of the jump and write the jump length to the 4-byte field back here. This simple do loop is easier to understand than the full-strength do loop a little farther down with qdo plus loop, unloop, and leave. we have instructions for a literal 3 and a literal 0. These three instructions move those two numbers from the data stack to the return stack, which is where the do loop keeps its loop control parameters at runtime. Then the loop body, then the code at the end of the loop that updates and tests the loop control parameters, then a conditional jump. After the jump, the loop control parameters are discarded. We have the case statement, strings with escape sequences, non-canonical mode, so the standard fourth word key can receive a character without echoing, number conversion, including double-celled numbers and numbers in various bases, and the rest of the fourth interpreter. We redefine dot to have the usual fourth behavior to show a number, and we call quit. Quit is a loop that refills and interprets repeatedly, much like the text interpreter. Interpret considers each word in the line and compiles it or executes it or tries to convert it to a number. So there you have it, a standard fourth for x86-64 made by hand. I know I didn't explain everything, but we did see the main structure. The fourth interpreter reads from standard input, so we can use it interactively. We may provide input to the fourth system from the keyboard. We have the usual Unix canonical mode line editing, just the basic features. The backspace key works. You can use Control-D to end the input stream, or Control-C to kill the process, or Control-Z to suspend the process. We may redirect input from a file, or use pipes. Here's the fourth 2012 test suite. Often we might want to read from a fourth source file and then type more input into the standard input stream. This program demonstrates a little fixed point arithmetic and a solution to the FizzBuzz exercise. Thanks for watching. Please find useful links in the description.